Hello everyone, my name is Stephanie Woodruff, and today I'll be demonstrating various molecular geometries using balloons. Each model will represent different shapes that molecules can form based on their bonding pairs, which are the areas where atoms are bonded, and lone pairs, which are the areas where electrons are not involved in bonding. I'll explain the total number of bonding areas, non-bonding areas, the electron domain geometry, and the molecular geometry for each model. The center of the balloons, where the balloons are tied, will represent the central atom. The balloons themselves represent like an electron cloud, and each element is at the end of the balloon. Yellow balloons will represent lone pairs in many cases, and for cases where we use 6 balloons, pink balloons will represent the lone pairs. So let's get started. First, let's talk about linear geometry. An example molecule would be carbon dioxide, or CO2. It has 4 bonding areas, 0 non-bonding areas, or lone pairs, 2 electron domains. The electron domain geometry is linear, and the molecular geometry is also linear. In a linear geometry, the central atom carbon is connected to 2 atoms of oxygen with no lone pairs on the central atom. Here I'll use 2 balloons representing the double bonds between carbon, the central atom, and oxygen at the ends of the balloons. The balloons will be aligned in a straight line at a 180-degree angle. Another example of a linear bond molecule is hydrogen cyanide. Hydrogen cyanide has 2 bonding areas. It has 0 non-bonding areas, or lone pairs. It has 2 electron domains, and the electron domain geometry is linear, as well as the molecular geometry is also linear. For hydrogen cyanide, the central atom, carbon, is bonded to hydrogen and nitrogen, forming a triple bond with nitrogen. I'll use these 2 balloons to represent the bonds, and the balloons are arranged in a straight line showing the 180-degree angle typical of linear geometry. Next, let's talk about trigonal planar geometry. So an example molecule is boron trifluoride, or BF3. It has 3 bonding areas, 0 non-bonding areas, or lone pairs, 3 electron domains, and the electron domain geometry is trigonal planar. The molecular geometry is also trigonal planar. For the trigonal planar shape, we'll be using 3 balloons for the bonds, all attached to the center, which represent boron. The bonds are spread out evenly, forming a flat triangular shape, and the bond angles of 120 degrees. Each balloon represents a bond with fluorine atoms. This configuration is symmetrical and has no lone pairs on the central atom. Another example molecule is sulfur dioxide, or SO2. It has 2 bonding areas, 1 non-bonding area, or 1 lone pair, 3 electron domains. The electron domain geometry is trigonal planar, and the molecular geometry is bent. The molecular geometry is bent. For sulfur dioxide, the central atom, sulfur, has 2 bonding areas and 1 lone pair. So here we will be representing the oxygen atoms and the 1 yellow balloon for the lone pair. The lone pair pushes the bonded pairs down, creating a bent shape, with the bond angles slightly less than 120 degrees. Next, let's talk about tetrahedral geometry. So we are going to use these balloons, and an example is methane, CH4. It has 4 bonding areas, 0 non-bonding areas, or lone pairs, 4 electron domains, and its electron domain geometry is tetrahedral, and the molecular geometry is also tetrahedral. A tetrahedral shape involves 4 bonding areas with no lone pairs. Here I'll be using 4 balloons for the bonds attached to the central carbon atom here in the center. They will spread out in a 3-dimensional shape with a bond angle of 109.5 degrees. Each balloon represents a bond with a hydrogen atom. This arrangement maximizes the distance between the electron pairs, minimizing repulsion. Another example is ammonia, or NH3. It has 3 bonding areas, 1 non-bonding area, or 1 lone pair, 4 electron domains. Its electron domain geometry is tetrahedral, and its molecular geometry is trigonal pyramidal. In trigonal pyramidal geometry, the central atom, nitrogen, has 3 bonds, or 3 balloons, and 1 lone pair, the yellow balloon. The lone pair pushes the bonded pairs downward, forming a pyramidal shape. So this pushes down, and the bond angles are slightly less than 109.5 degrees due to the lone pair repulsion. Each balloon represents a bond with a hydrogen atom. Next, we're going to talk about bent geometry. So, a good example for bent geometry would be water, or H2O. It has 2 bonding areas, 2 non-bonding areas, or 2 lone pairs, 4 electron domains. The electron domain geometry is tetrahedral, and the molecular geometry is bent. For the bent shape, we'll be using the 2 balloons for the bonds representing the hydrogen atoms, and the 2 yellow balloons for the lone pairs. Our center will be our oxygen. The lone pairs exert a repulsion force, pushing the bonds closer together and creating a bent shape with a bond angle about 104.5 degrees. As you can see, this is our H2O, or water molecule. Another example molecule is ozone, or O3. It has 2 bonding areas, 1 non-bonding area, or 1 lone pair, 3 electron domains, and the electron domain geometry is trigonal planar, and the molecular geometry is also bent. For ozone, the central atom, oxygen, has 2 bonds and 1 lone pair. The lone pair pushes, so we're going to use the same one. Let's ignore this second lone pair. We just have 1 single lone pair for ozone, and the lone pair pushes the bonds closer together, resulting in a bent shape. And the bond angles are slightly less than 120 degrees. Now let's talk about trigonal bipyramidal. So we are going to need 5 balloons. Okay. Excuse me. An example molecule is phosphorus pentachloride, or PCl5. It has 5 bonding areas, 0 non-bonding areas, or 0 lone pairs, 5 electron domains. The electron domain geometry is trigonal bipyramidal, and the molecular geometry is also trigonal bipyramidal. In a trigonal bipyramidal shape, it uses 5 balloons to represent the bonds. 3 balloons form a flat triangle around the central atom, phosphorus, like a flat plane, and the other 2 are positioned above and below the plane. This shape is like a triangular pyramid on top and below the central plane. Each balloon represents a bond with a chlorine atom. This geometry is common for molecules with 5 bonding pairs and no lone pairs, such as phosphorus pentachloride. So if you look, we have this at the top and at the bottom. The balloon doesn't want to stay in that shape. Another example molecule is sulfur tetrafluoride, or SF4. It has 4 bonding areas, 1 non-bonding area, or 1 lone pair, and 5 electron domains. The electron domain geometry is trigonal bipyramidal, and the molecular geometry is seesaw. In the seesaw shape, I'll use 4 balloons for the bonds representing the fluorine atoms, and 1 balloon for the lone pair. The lone pair is positioned in the central plane, like the middle balloon, in a 3-balloon arrangement, pushing the other 4 balloons into a seesaw shape. The bond angles are slightly distorted due to the lone pair repulsion. So if you look here, these are like the legs of a seesaw, and this is like where children would sit on either side here, which gives us kind of like a seesaw type shape due to our lone pair pushing its repulsion down. One other example molecule is chlorine trifluoride, or ClF3. So we're going to need these 3. And it has 3 bonding areas, 2 non-bonding areas, or 2 lone pairs, 5 electron domains, and the electron domain geometry is trigonal bipyramidal, and the molecular geometry is T-shaped. In a T-shaped geometry, the central atom chlorine is bonded to 3 fluorine atoms. So these would be our 3 fluorine atoms, with 2 lone pairs positioned in the plane. So these are going to press against this. The lone pairs are going to push against the blue balloons. And in this model, you'll see 3 balloons for the bonds, representing the fluorine, and the 2 yellow for the lone pair. The lone pairs push the bonds into a T shape. Let me try to get a better view for you guys here. Oh, sorry about that. Some quirky balloons here. Okay. So we have our lone pairs over here on the side at a right angle, and it pushes our blue balloons into a T-type shape. Hand out of the way here. There we are. I don't know if you can see that. And these are our lone pairs pushing the repulsion, creating this T shape. Oh, those balloons didn't want to cooperate very well, did they? Okay, so our next discussion is going to be on the octahedral geometry. Octahedral geometry, a good example is sulfur hexafluoride, or SF6. It has 6 bonding areas, 0 non-bonding areas, and 6 electron domains. The electron domain geometry is octahedral, and the molecular geometry is also octahedral. For the octahedral shape, we're going to use 6 balloons to represent the bonds. 4 balloons will form a square around the central, so the central atom in the middle being sulfur, like a cross, and the other 2 will be positioned above and below the square. So if you look at it head on, you can see a square shape here. And then we have this atom at the top and at the bottom. Each balloon represents a bond with a fluorine atom. This geometry is common for molecules with 6 bonding pairs and with no lone pairs, such as sulfur hexafluoride. You can see that square shape. And we're using a lot of colorful balloons on this one here. Another example molecule is bromine pentafluoride, or BRF5. It has 5 bonding areas, 1 non-bonding area, or 1 set of lone pairs, 6 electron domains, and the electron domain geometry is octahedral, and the molecular geometry is square pyramidal. For the square pyramidal shape, I'll use 5 balloons for the bonds representing the fluorine atoms. And we're going to use 1 pink balloon. Sorry about that. Balloons everywhere. Balloons for everyone. And 1 pink balloon for the lone pair. So we have a set of 5. And then we have 1 pink balloon that's going to represent our lone pair. The lone pair is positioned at the top of the square, pushing the bonded pairs into a square pyramidal shape. The bond angles are slightly less than 90 degrees due to the lone pair repulsion that is pushing down on these fluorine atoms. So as you can see, this is our lone pair at the top, our pink, and it's pushing down repulsion on our fluorine atoms. Now, let's see. Now let's talk about square planar geometry. An example molecule is xenon tetrafluoride XeF4. It has 4 bonding areas, 2 non-bonding areas or 2 lone pairs, 6 electron domains. The electron domain geometry is octahedral, and the molecular geometry is square planar. For the square planar shape, I'll use 4 balloons for the bonds, which are representing the fluorine atoms. And we are going to use 2 yellow. Let's see, where did our yellow atoms go? Bear with me. Okay, so we are going to use 4 balloons for the bonds representing the fluorine atoms. And in this case, we're going to be using our 2 yellow balloons to show our lone pairs. The lone pairs are positioned opposite of each other and pushing the bonded pairs into a flat square arrangement. So you can see our square arrangement of our fluorine atoms. And you can see our lone pair at the top and at the bottom. This geometry is often seen in molecules with 4 bonding pairs and 2 lone pairs, like platinum chloride, and the lone pairs are located above and below the square plane, minimizing repulsion and maintaining the 90-degree bond angles between the bonded pairs, 90 degrees. Another example molecule is platinum chloride. And platinum chloride has 4 bonding areas, 2 non-bonding areas or 2 lone pairs, 6 electron domains, and the electron domain geometry is octahedral, and the molecular geometry is square planar. For platinum chloride, the central atom is platinum, and it is surrounded by 4 chlorine atoms and has 2 lone pairs. Using the 4 balloons for the bonds and the yellow balloons for the lone pairs, this model will also form a flat square, just like our xenon tetrafluoride atom, molecule. So almost exactly the same. In conclusion, we've explored various molecular geometries using balloons to represent bonding and non-bonding areas. By visualizing these shapes, we can better understand the 3-dimensional arrangements of atoms in molecules and how lone pairs influence these structures. Each geometry, from linear to octahedral, demonstrates how electrons arrange themselves to minimize repulsion and achieve stability. Using balloons makes it easier to see how lone pairs, yellow or pink balloons, push bonding pairs into different shapes. Understanding these geometries is crucial in predicting the behavior and chemical properties of molecules in different chemical reactions. Thank you for watching, and I hope that you enjoyed this demonstration. Thank you for bearing with me with the balloons, and I hope that this has helped you grasp the concepts of molecular geometry. Until next time.